So we're delighted to celebrate the third anniversary of the virtual seminar with a talk by Simon Salamon of King's College. And he will speak on the flag manifold SU3 mod T2 and its subvarieties.
Okay, thank you, Caroline, and to the organisers. As I was saying a few minutes ago, I feel a bit guilty about this because I haven't followed in a regular way the series, although I've enjoyed the talks. I have managed to follow, and as you say, it's a good thing that this is going on. So what I want to talk about today is a sort of combination of complex projective, fairly elementary complex projective geometry and Riemannian geometry. And well, the first thing to say is this is joint work with Altavilla, Ballico, and Brambilla. And I gave I'm sort of resurrecting in some sense a talk I gave a couple of years ago, although there's more in this talk. And perhaps the thing to say first, it is a bit of a mixture of complex and algebraic geometry, complex and Riemannian geometry, I should say. I'm trying to find my pen. In a sense, I'm going to start with some projective geometry, and then there'll be I'll switch to sort of talking about twistor theory, because you may think it's a bit simple to talk about the flag, sort of lowest dimensional flag manifold, but I want to convince you that even with that example, there's quite sort of a rich theory and lots of open problems. So I want to talk about really the flag manifold from the twistor point of view, in which you have this twistor projection, which is not holomorphic. And I first came to understand this when I was many years ago, when I was trying to understand harmonic maps and the use of harmonic maps and using flag manifolds to sort of classify harmonic maps of surfaces. So I'll be talking a bit about the sort of twistor background, and then I'll go back to sort of the game of trying to find how many twistor fibers there are in certain surfaces in the flag manifold. Mentioning as I say, I gave this similar talk in a memorial conference for Vesentini, and that reminds me of his collaborator Calabi, who will be, as many of you know, 100 in a week's time. And of course, Calabi was very much on the interface of complex geometry and Riemannian geometry. And you know, I particularly profited from his work on minimal surfaces in spheres, which sort of introduced the use of twistors in that context. So let me start in an elementary way. Let me just try and see if I can get my pen. Oh yes, that's good. So here's the definition of the flag manifold. Of course, a flag, we're talking about flags in C3. So a flag is just a point, well, a line. If we use vector spaces, it's a line in a two-dimensional subspace inside C3. If we work projectively, then it's like having a point in CP2, the complex projective plane, contained in a line. Okay, so we have that's the notation here. So we have a point in a line in CP2. And of course, that setup sort of corresponds to having a double fibration. You're sort of setting this up as a double fibration. So you have to be a bit patient with me to begin with while I get used to the new setup. So I'm defining the flag manifold as really a subset of CP2, strictly speaking, times its dual. That's here. And the dual, of course, if you like, is a set of planes in C3. But it's a good exercise when you're doing linear algebra, teaching undergraduate linear algebra. You have to be very careful to respect the distinction between rows and column vectors. And I taught linear algebra for many years, and I was also very keen to do this, and it helps do calculations with the flag manifold to keep that distinction very clear. So for me, I'm going to think of points of CP2 as sort of row vectors, points of the dual as column vectors. And there's a slight abuse of notation here, means I'm confusing projective classes and vectors. But basically, I'm saying that flag manifold is just a set of these pairs for which the row vector times the column vector is equal to 0. That's the easiest way to say it. And so naturally, we have these. It's a complex manifold. And we have these two these two holomorphic projections, one to the points and one to the lines. So that's always at the back of my mind. I'm thinking of the flag manifold as embedded in, well, essentially the product of two projective planes. And then the other thing, we're going to start talking soon about surfaces in the flag manifold. So having this setup enables you straight away, you can pull back the standard line bundles on the projective planes and talk about divisors of by degree AB, which just means sort of power of A on the left and a power of B on the right. And for example, if you want to say what is the canonical bundle of the flag manifold, that would be the sort of 3 0 forms, and this would be this is the same. This is the same as O minus 2 minus 2, for example. Okay, that's the basic setup. And then another thing you can say, I mean, if you're more used to thinking about the complex projective 3 space, in some sense, in some regards, it's easy to talk about the flag manifold. You see that there's a natural contact structure, holomorphic contact structure, which basically is a holomorphic one form with values in this line bundle, O11. And I can define it just to be P times DL or minus dP times L. And that tells you immediately that the fibers of the two projections I talked about are, lie in the contact distribution. Because if L is constant or P is constant, the contact form is 0. The annihilator of the contact form is the contact distribution. So some of you may be more used to thinking about this on the complex projective 3 space, but it's the same sort of setup. And in fact, there's part of the motivation of this talk is to try and do things on the flag manifold that have already been done on complex projective 3 space. And the point is these two threefolds are both Fano contact manifolds. And Fano contact manifolds are related also in high dimensions to they're the twistor spaces of quaternion Kähler manifolds, and something Joe Wolf understood long time ago. So anyway, as far as the flag manifold is concerned, this is contact structure because if you try and understand what d theta means, you can understand that theta wedge d theta is nowhere 0. And this will have values in, I already told you what the canonical bundle was. This would have values in the canonical bundle tends to do over 2, 2, which is trivial. So that it makes sense. This would be, it's value just a constant, non-zero constant. Okay, and the other thing to say here is that, remember, the point of the flag manifold is a pair PL, and you can act naturally on that by, if we were just in P2 cross P2, you could act separately by SL3C or the projective general linear group on both factors. But since we have this equation that the flag manifold the points have to satisfy this equation that PL is equal to 0, so the two matrices have to really be, one is the inverse of the other. So we're left with the symmetry group PGL3C, essentially. So this acts naturally on the flag manifold. And if instead of writing PL is 0, we multiply the column vector by the row vector, we get a 3 by 3 matrix, a rank 1 matrix. And we can think of that as defining a map of the flag manifold into, well, it would appear to be CP8, but because the trace is 0, so it's really embedded in, the flag manifold gets embedded in CP7. And that's some sort of holomorphic moment map, because you can think of C8 as the Lie algebra SL3C. So it's worth bearing that in mind. We'll see a real version of the moment map later on. So let me start then with a discussion of the sort of most elementary objects you can define in the flag manifold. We've already talked about these two fibrations. So we've got various lines, the fibers of pi1 and the fibers of pi2. The next simplest thing really is to define these surfaces, which are just defined by these equations. So these sort of linear surfaces. So for example, Q is written here on the left because it refers to we've got this fibration, remember F fibering on the left to CP2, and then on the right to the dual space CP2 star. And Q is always a point of CP2 and L is a point of the dual space. And so if we use this equation, we fixed Q is fixed here. So we're looking for the pairs PL for which QL is 0. And that's really the same thing. I'm talking about the first Hertzsprung surface. That's the same thing as saying we take Q defines a line. Q defines a line in the dual space. So we can take the inverse image of that with respect to pi2. And then we can project that surface, that is the first Hertzsprung surface, we can project it down by pi1. And most points of this CP2 will just hit that surface in one point. But if we take the point Q itself, then we'll have the whole fiber of pi1 contained in this first surface. So what's going on here is we're just really blowing up if we use pi, the first surface is just the inverse image of a line under pi2. It's really just blowing up the point Q relative to pi1. So we just get this Hertzsprung surface of first type in which we've just taken CP2 and blown up one point. Or we can do exactly the same thing on the other side and blow up a point of CP2 star. So we have these two sort of linear surfaces, families of surfaces in our flag manifold, and we can do all sorts of things. We can intersect them, for example. So if I intersect them, two of these Hertzsprung surfaces, I'm just going to get a curve. I'm going to get a curve of bi degree 1, 1. I mean, it's first of all, I define the bi degree of surfaces. I can then define the bi degree of curves by intersection with those surfaces. And so I have this important class of curves denoted LQM, and it's just given by this very natural, sort of straightforward linear algebra, really, given by these equations. But we've also got PL is in the flag, so that means PL is also equal to 0. And that's the intersection of these two linear surfaces. And typically, this will be a smooth surface, except if QM is 0, then it would just be the union of two of our fibers. Okay, so let me just give this definition because these objects will be important for what follows. managed this before when I was practicing. So let me just record this definition. By a line in the flag manifold, I just mean one of these fibers, a fiber of pi1 or a fiber of pi2. So actually the fiber of pi1 has pi degree 0, 1. It goes the opposite way to what you might expect. Fiber of pi2 has pi degree 1, 0. But I'm mostly interested in what I call conics, that is these curves LQM, typically smooth, but including the reducible possibility. So again, this is just described by the underlying linear algebra of row vectors and sort of column vectors. So a conic is really, instead of lying in P2 cross P2 star, it lies in P1 cross P1 star. And so I'll be studying later on, we'll be trying to count the number of these conics in surfaces. So this is really the key definition for what I'm going to say later, well, particularly the conic. Okay, now what about, that's sort of fairly easy. What about sort of moving on to quadratic objects? Well, I'm going to say a lot later about surfaces of pi degree 1, 1. And they're easily defined, again, with this sort of linear algebra setup, which I want to emphasize. Instead of the flag manifold, of course, is defined by the equation PL is equal to 0. P, remember, is a row vector and L is a column vector. But if we insert a matrix in the middle, then we can define, this will define a surface in the flag manifold corresponding to this 3 by 3 matrix A. And that will be a surface of pi degree 1, 1. So the thing is, if you have a matrix A, of course you can subtract any multiple of the identity because of this equation. So we're really looking at sort of matrices A, sort of pencils of these matrices, in which you can add or subtract any multiple of the identity. And you can, again, it's sort of basic linear algebra. You can use Jordan form to understand that, projectively speaking, we have the following classes of such. So each of these matrices modular the identity will define a surface of pi degree 1, 1. And you can always make the dots mean 0 here, so you can always make the first eigenvalue here, for example, 0. This is the diagonal case here, which is the most important one really for this talk. But there are these other sort of more degenerate cases. And the other thing to say is that, so only in the first case are we talking about, this is the diagonal case, we're talking about smooth surfaces. The second case is rather elementary, the surfaces are just reducible. The third case is A3 and A5, that's more complicated, but the surfaces have a singular point. And the other thing that's worth saying, I haven't fully understood why this is true, but lambda, because of this, because of the symmetry involved here, and of course in this talk I meant to emphasize symmetries, we can sort of permute the eigenvalues. And so lambda turns out really to be a cross ratio. That is to say that projectively speaking, when I say projectively, I just mean by conjugating the matrix by SL3C. So up to conjugation by SL3C, lambda can be changed to one of the other 5 versions of the cross ratio. So those values of lambda all correspond, projectively speaking, to the same surface. And so if you want to, I'll say a bit more now about these 3 columns, if you like. So in the smooth case, because in the smooth case, it's easy to see by looking at the eigenvectors of the matrix A that they define points, 3 points in CP2 or 3 points also in the dual CP2. And what's going on here is that this surface is just blowing up P2 in those 3 points. And the blow up of CP2 in 3 points is a Del Pezzo surface or so was the Hertzbruch surface, but this is a Delpezza surface of degree 6. And so what's going on here is that these surfaces of type 1,1, these smooth surfaces of type 1,1, come about by blowing up 3 points in P2 on the left and blowing up 3 points in P2 on the right. So you have these exceptional curves. So I have these three. If I start on the left with the 3 points on the left, the points correspond to eigenvectors. I get these, the 3 points, of course, when you take the fibers, they're skew, they don't intersect. So you get 3 disjoint exceptional curves in this surface S. And then you've got the 3 points on the right, which you can blow up, and they give you 3 other exceptional curves. And so you get this hexagon of exceptional curves in this Delpezza surface. So this is the sort of underlying projective geometry of these surfaces. Later on, we'll be talking about the sort of more Riemannian features, but this is the underlying projective geometry of these smooth surfaces of type 1,1. And then the other 2 columns, as I say, A2 and A4, that's just the union of 2 Hertzbruch surfaces, and the intersection could either be smooth or not smooth, as I said earlier. So that's A2. Smooth intersection is A2, and reducible intersection is A4. And A3 and A5 correspond, I think, to so-called weak Delpezza surfaces, although not smooth ones. There's one singular point in both cases, in each case. But the other thing I would just want to emphasize is that this is a projective classification. Later on, we'll actually need a much finer classification under the unitary group. Rather than SL3C, which is what I'm talking about at the moment, or if you like, PGL3C, I want to reduce to PS, well, I'll just say SU3. And so really all this classification of these 5 classes, it becomes much finer when you do it with respect to, instead of conjugating by SU3C, you conjugate by SU3. And I won't be saying anything more about that classification today, but it does underlie what will come later. Okay, I don't know if I should pause for a minute. I'm sort of settling down and ask anything. If not, I'll just go straight on. Okay, so I want to now sort of bring in this unitary structure, or if you like, what I'm really doing is I'm passing from the sort of complexly group to the unitary group SU3. Now, it's worth remarking that before we do that, we already have a sort of form of cross product, because there's a natural, the SL3C structure allows you to take 2 row vectors and take the cross product of 2 row vectors. Well, here I've done it with lines, actually. Take the cross product of 2 lines and form a row vector. Okay, so the cross product of 2 lines, the cross product of 2 column vectors is a row vector, and that operation makes sense because we have this SL3 structure, or the cross product of 2 row vectors is a column vector, and that's just geometrically. That's the obvious fact geometrically, that if you have 2 lines, you can look at their point of intersection. So the cross product just defines the point of intersection. So we have that already, but if we reduce to SU3, we can also take the conjugate transpose of a row vector and get a column vector. So having SU3 enables us to actually convert row vectors to column vectors, which is something I hadn't done before. So that's what we now have available, and using that fact, we can introduce this third twistor vibration, which is this vertical map here. So what I'm doing, as you should probably, many of you understand, is I'm just, instead of thinking of a flag as a line in a 2-dimensional subspace in C3, I'm now using the unitary structure to think of a flag as just a decomposition of C3 into 3 orthogonal lines. And so given a flag, rather than thinking of it just as a sort of one-dimensional subspace in a two-dimensional subspaces, I'm just thinking of it as 3 one-dimensional subspaces. So I've got 3 projections, it's fairly obvious. But it's a good idea to sort of distinguish what you might call the algebraic geometry, which is at the bottom of this picture, these holomorphic mappings, these are holomorphic, to this new projection I've introduced. And in terms of row vectors and column vectors, I'm just taking PL, which is a row vector and a column vector, and I'm just converting the row vector into a column vector, and just applying this cross product to get a row vector. That's just a fancy way of taking the sort of orthogonal complement of the P and the L star. So this is the so-called twistor projection, which we're going to study. So perhaps it would be more logical, since this is pi1, this is pi2, to call pi what I call pi, this new one, pi0, but it doesn't matter. Here I shouldn't, the other thing to note is here, this has now become actually CP2, not CP2 star. I don't need the dual anymore because I can use this transpose conjugate to convert. That's why this is L star and not L. So might be a bit of confusion there, but okay. Now there's one other thing which we've got this SU3 symmetry, but we also have an obvious sort of threefold symmetry on the flag manifold. So first of all, here I'm just saying what I've already said, actually. I'm now thinking, rather than thinking of a flag as sort of P contained in L, so this is P here, and these two would correspond to what I called L. I'm thinking of it just as the sum of 3 lines. If you prefer, you can call that L0. That's the idea of these 3 projections. But we can also sort of commute these 3 fibrations, and algebraically, the reason one can do that, it comes about from the Weil group of SU3. So the Weil group, that's the elements that we fix. So of course, if we think of the flag manifold, we can think of it as a homogeneous space. It's SU3 over T2, where I'm thinking of T2 as a maximal torus of SU3. And the Weil group, the normalizer of that maximal torus divided by the torus, is just the group of permutations, S3. And that group will act on the flag manifold by just permuting it will in particular, well, it will just permute, if we think of a flag now as three lines, it will just sort of permute those 3 lines. But it's important to realize I'm not thinking of the Weil group as a subgroup of SU3 acting on cosets on the left. If I think of a coset here, an element of the flag manifold could be thought of as a coset like this. I'm not putting an element of Weil group on the left, I'm really putting it on the right. So I'm putting it on the right, or equivalently, I'm sort of putting the Weil element there. So that won't be a subgroup of the isometries, or it won't be a subgroup of SU3. So it's sort of acting in an outer sense. And so in particular, you can permute the one element of our group will permute the vibration pi1 and pi2. Will permute these 2 lines, and that will be an anti-holomorphic, with respect to our original complex structure, that will be an anti-holomorphic involution, and that will correspond to, I mean, that's the anti-holomorphic involution that defines really the twistor lines. That's the vertical. The lines that are invariant by J are the twistor fibers. That's the fibers of the vertical vibration. And J commutes with SU3. The other thing, I mean, if you tuned in to hear about G2 and nearly Kähler manifolds, of course, the flag manifold is one of these basic examples of homogeneous nearly Kähler manifolds, and they can be used to construct G2 metrics by taking the cone, and also they're more sophisticated constructions now of G2 metrics with holonomic G2 known that involve the flag manifold. I'm not going to talk about that today, nor am I going to really talk about any particular metrics on the flag manifold. So in some sense, the most symmetric metric would be the nearly Kähler metric, which is invariant by this W action, and also its corresponding almost complex structure, whereas the standard Kähler metric is sort of prefers one of the vibrations. But I'm sorry, I won't be saying more about that today. So another way of thinking of the flag manifold, I mean, this is all sort of elementary, but it's not a holomorphic way of thinking, so it might not be so familiar. If you think in terms of sort of homogeneous spaces, you know that the tangent space of the flag manifold, you can just think of it as the sort of complement of the Lie algebra of SU well, I've complexified here, the Lie algebra of SU3 quotiented by the Lie algebra of the maximal torus, but sort of informally speaking, that's SL3C minus C2, and or think of it really as sort of GL3C minus C3, but C3, GL3C is C3 star tensor C3, and we've already said that a point of the flag manifold divides C3 into 3 lines. So if you put that all together, you see that the tangent space is really, when you've complexified it, you get the sum of these 3 pieces, and that's just saying that the real tangent space is just the sum of 2 planes, which correspond to the sort of fibers, 3 fibers. But now you see you can choose invariant, there are various ways of choosing invariant complex structures, because these have all natural orientations. So if I orient each of these R2 in any way I want, I'll get an almost complex structure which is invariant by SU3. And an orientation is equivalent just to choosing one of these two summands in each parenthesis. So if you do that, you see that that gives you a total of, strictly speaking, 8 almost complex structures, but up to sign only 4. 3 of those will be integrable and 1 will be non-integrable, which is the nearly Kähler one. So for example, if you want the standard complex structure on the flag manifold, that means the 2 projections to CP2 and CP2 star are holomorphic. So that really corresponds, these correspond to the tangent spaces of these CP2 on the left and CP2 on the right. And if you add those together, you'll get this combination, 1 line in common. And so that to get this, I've distinguished this orientation, this orientation, and this orientation here. That would correspond to the standard complex structure. Why do you know that's integrable? Well, if you just look at this thing here, if you want to sort of take Lie brackets, you can only sort of contract something with its dual. And the only thing you'll see in common here would be the L and the L, and the L star. So if you contract L with L star, you'll be left with L1 star L2, which is this. So that, because I've included it this way around, that means this is integrable, this structure. But had I chosen this one, it would have been non-integrable. And there's a fancy way of, I can't resist saying this, there's a fancy way of saying that, which doesn't, excuse me, isn't terribly useful in 3 dimensions, but when you do higher flag manifolds, you can use these sort of so-called tournaments, which are just digraphs, directed graphs in which are a complete directed graph. So you have a number of vertices and all possible edges joining those vertices, and you choose any arrows you want. It's like sort of having so many players and having a round robin tournament in which everyone plays everyone else and the arrow indicates who wins. Now, if the choice, this is just repeating the choice I just made. So I can represent that choice. These, in a sense, the vertices of this triangle correspond to the three lines L1, L2, L or L0, and the edges correspond to the subspaces of the tangent space. So my choice here, L star L2, I've got the arrows actually all the wrong way around here. So L star L2, I should really think of that arrows going that way. L1 star L2, the arrows going that way. L1 star L, the arrows going that way. That's not a, notice this is not a cycle, and that tells you that the thing is integrable. The almost complex structure is integral. But you can also determine the nature of these projections. You see pi1, you sort of, when you project to pi1, it's like contracting, it's sort of like contracting this edge here. So you're left with two arrows going in the same direction. And that's sort of telling you that pi1 is holomorphic and pi2 is anti-holomorphic. And if you look at pi, this twistor projection, you see with the problem with pi is that I've got an arrow going this way and I've got an arrow going that way. So when you contract this edge here, the things are not compatible, and that's telling you it's not holomorphic. So that's just a bit of a joke, but it becomes useful in higher dimensions. And so as I think I mentioned before, you can use these flag manifolds to understand. Well, in particular, you can use flag manifolds to understand the sort of theory of harmonic maps of surfaces into CP2 or higher, CPN, I should have said in general, because you can sort of take derivatives and lift these maps to a flag manifold, and then you can project them using another projection. And you could start with a holomorphic map, which is obviously harmonic, into the flag manifold. You take a sort of derivative and sort of Gauss map sort of thing, and that gives you to the flag manifold. Then you can take one of the other projections, and because of the theory of if you take the non-integrable almost complex structure, when you project, you'll always get a minimal surface. So you can generate non-holomorphic minimal surfaces that way. And the ideas here also sort of date to Calabi's famous theorem on minimal surfaces in spheres, which was in general differential geometry 1. But this idea of using these tournaments I did with Van Boerstel. Okay, that's a bit of a digression. Now, let me finish this. This was meant to be the sort of halfway point. Never mind. Let me finish this section by just sort of bringing in some true surface, the Riemannian sort of surface theory. Remember, we're talking about I'm now talking about this twistor projection. So I've got the flag manifold and I have this twistor projection, this non-holomorphic projection, which I call pi to CP2. Not the other two, which I started the lecture with. So the question is, if we take one of these fibers here, so-called twistor fibers, a fiber of pi, this is not a holomorphic projection. So the normal bundle of one of these fibers will not be trivial. Holomorphically, it's O1 plus O1, which means it has a sort of real four-dimensional deformation space. So if we deform this fiber has, it's a special type of, I've said it here. So remember I talked about these conics earlier on. These are these these are these curves of by degree 1, 1. These twistor fibers are special examples of 1, 1 curves. They're 1, 1 curves. Instead of having generally LQM, if I take M to be Q star, that means the conjugate transpose, I get one of these twistor fibers. So of course I'm using the unitary structure here. So I have these twistor fibers, but I can deform them. I can change Q star and put a more general M, as I had before, and then I get a curve which is not vertical with respect to this fibration. How does it project to CP2? And I'm going to tell you now. So I'm hiding quite a lot of calculations here, But it turns out that if we take one of these curves, so LQM, not QQ star, we can define this matrix here. So it's QM as a scalar times the identity minus MQ, which is again a 3 by 3 matrix. And then I can say that the projection of this 1, 1 curve is the set of points in CP2 that satisfy that equation, projectively speaking. You can check that this will be this would just be 1 point if Q is equal to Q star. In any case, when you write this in coordinates, it really becomes a very simple object, as you might expect, because if you remove the sort of complex geometry, it's just the projection is just going to be I mean, these fibers are all projective, are all topologically two spheres. So when you project one of these things, it's not surprising that if you use affine coordinates in C2, say in CP2, you get just the equation of a sphere. Okay, but what we're interested in is not, we're not in Euclidean space, or we're not in S4, we're using the Fubini-Studi metric for the complex projective plane. So the question is, what does this surface look like relative to the Fubini-Studi metric? And the answer is it looks something like this, typically. You see, the point is these don't forget the structure of these conics, as I called them, LQM. So if M is equal to Q star, when we project this, we just get a point. When at the other extreme, we have the possibility that we get these can become reducible. If QM is equal to 0, remember, so of course if M is Q star, it can't be 0, but if QM is equal to 0, this is just the union of two of the other fibers. And in that case, what's going to happen is we just get two spheres stuck together. Of course, that would be when QM is 0. So somehow what happens is you can deform according to the cross product Q cross M star. You'll either have a point or it will get bigger, and you know, halfway between the point and this dumbbell thing, you'll have a sort of peanut shaped surface, peanut shell shaped surface, and eventually the two spheres will stick together. And the interesting thing about this is they're not really talking about any twistor theory here. I'm just telling you what this equation looks like relative to the Fubini-Studi metric. It's isometric to the surface of evolution. There's still an S1 symmetry here because I'm not doing anything. If you look at this equation, I'm not doing anything really to the Z2. There's still this S1 symmetry acting on Z2. So there's this underlying S1 symmetry coming from the Z2 coordinate. It's a 1, 1. We're projecting a 1, 1 curve, so we expect something somehow of degree 2 in some sense, and that's what you get. Okay, now the third section, and I don't mind really if I don't have much time for the fourth section, because that was more just a matter of the game of counting curves. So let me try not to rush this part. I've been talking about thinking of this, so I defined this vertical projection just using linear algebra cross products, or I explained if you want to think of flags, it's just sort of with this S3 symmetry, it's natural that you have this extra third vibration. But if you're used to twistor spaces of 4 manifolds, you can of course understand this in a different way. Namely, let me explain this in the case of CP2. So we did start with CP2, and we know that we have this CP2 and we have this flag manifold. I'm afraid I'm doing it backwards here, but it doesn't matter. We have this flag manifold. You normally put the bigger space on top. But anyway, here we have this flag manifold and this twistor projection to CP2. If you think of CP2, I've been talking about, I've mentioned the Fubini-Studi metric. If you take CP2 as a Riemannian 4 manifold, it has a standard orientation because it has a standard complex structure, which I'm going to call I, and that really can be thought of as positively oriented. So if you take the space of two forms, on any Riemannian four manifold, it always splits as λ2 plus and λ2 minus. But in the case of Hermitian manifold, in this case a Kähler manifold, you know that if you choose the standard complex structure, you get the Kähler 2 form, you think of that as positively oriented. So λ2 plus splits as just that and essentially the forms of type 2, 0 and 0, 2. This is just the real vector space underlying the canonical bundle. And then λ2 minus are just the primitive 1, 1 form, sort of as a real vector space at each point. And then, you know, I mean, we forget about integrability for the moment. We can look at λ2 plus and λ2 minus. These are rank 3 vector bundles. Of course, this is 6 at each point. This is 6-dimensional. This is 3-dimensional, 3-dimensional. So we can look at these sphere bundles, the 2 sphere bundles in λ2 plus and λ2 minus, and those are so-called twistor spaces in general. And each of these really, if you take a point, if you take a unit, for example, if you take a unit anti-self dual 2 form, that defines an almost complex structure on the base, in this case CP2. So each point of this bundle, if you take Z, I'm talking about Z minus here, which fibers, I'm doing the fibration the other way here. I'm doing it backwards. I'm talking about Z minus, which fibers over CP2, and each point of Z minus, this is a 2-sphere bundle, the fiber is a 2-sphere. Each point can be thought of as unit anti-self dual 2 form, and that defines an almost complex structure on CP2. And of course, we know that in this case, Z minus is the same thing as the flag manifold. And that's, one can use this construction, use the Riemannian, the Levi-Civita connection to build a natural almost complex structure on Z minus. And you can ask, or you can start with an arbitrary Riemannian four manifold and ask, when would this natural almost complex structure be integrable? And the answer is well known. It will be integrable if the what's in the next paragraph, if the half of the vowel tensor W minus is identically 0. But in any case, before we talk about integrability, this bundle Z minus, because each point corresponds to an almost complex structure, it's sort of tautological that a section of this bundle over our four manifold, so this is M4, is our bundle in general with fiber S2. If we have a section, I'm sorry, everything's upside down, I didn't think of the consequence of that. If we have a section of this bundle, it just even locally over M, that would define an almost complex structure on M. We can then ask, when is this almost complex structure integrable? And it turns out there is a natural complex structure on Z minus, call it sort of blackboard J, and this section defines an integrable complex structure on M locally if this section is a holomorphic section with respect to this J. Here I've called it J minus, but I'm always talking about the sort of one that can be integrable. So this almost complex structure J, which I've defined just really on, it will exist both on the sphere bundle in λ2 minus, also on the sphere bundle, it would be called J plus, obviously on the sphere bundle in λ2 plus. And it will be integrable only if the corresponding half of the vowel tensor is 0. So for the flag manifold, W minus is 0, but W plus is not 0. And so Z plus won't be integrable, even though it does have a sort of a Kähler section corresponding to the natural complex structure I. I just wanted to say, because I don't know how well known this is, that if the vowel tensor is not 0, if that half vowel, if the semi-vowel tensor is not 0, as in this case here, the twistor space the bundle can't be complex, the twistor, the J can't be integrable, but you could still have complex structures, but you can only have at most 4 or up to sign at most 2, because the complex structures, these sections I was drawing, they have to correspond to roots of the Weyl tensor. If you think of the Weyl tensor as sort of quartic polynomial on spinors, you can have at most 2, well, at most, up to sign at most 2 roots. So if the Weyl tensor is not 0, if it's not sort of self-dual, or anti-self-dual in this case, you can only have 1 or 2 complex structures up to sign. In the case of CP2, of course, the roots coincide and you just have 1, but there is the possibility that you could have 2. Okay, that was a bit of a digression. I'm sorry about that. But that's the sort of background in terms of, if you prefer, the sort of Riemannian geometry of understanding this vertical fibration. So using this idea, this sort of notion of these complex structures, what this really tells us is that if we, because of this interpretation I've just given you of the flag manifold as the twistor space of CP2 that parameterizes not just any orthogonal, not just any almost complex structures, but ones that are compatible with the metric, with the Fubini-Studi metric, which I call GFS. What it means is that if we have any holomorphic surface in the flag manifold, that will project, if it's on an open set in which we can project it bijectively to CP2, it will define a complex structure on CP2, not the standard one, but it will define an integrable complex structure that's compatible with the metric. So it's what you might call an orthogonal complex structure. And I've given this name Fubini structure. It's, I should have said Fubini-Studi, but in honor of the fact Fubini worked at my previous institution. So a Fubini structure simply means an orthogonal complex structure relative to the, on an open set of CP2, relative to the Fubini-Studi metric. And we'll forget the standard complex structure. So you can only have these sort of sections if they're negatively oriented. And the point is that this is one motivation for studying these algebraic surfaces inside the flag manifold. So if you have one of these surfaces, like one of these Hertzebruch surfaces, that will define on an open set of CP2 one of these Fubini structures, just an orthogonal complex structure, a non-standard orthogonal complex structure. And we know from the sort of theory of S4, CP3 and S4, that these orthogonal complex structures can be very interesting. So here's an example of this. I would just show this very quickly. If you did take a Hertzebruch surface, what happens is this, one of these Hertzebruch surfaces, here we're defining it by blowing up a point of CP2 with respect to the first projection, that will contain exactly 1 twistor fiber, as it turns out. If you remove that twistor fiber, then the Hertzebruch surface will map bijectively to the complement of CP2 using the vertical projection. And what that means is that you can take the complex structure on the Hertzebruch surface induced from the standard complex structure on the flag manifold and get a complex structure on the complement, which is CP2 minus a point. Well, that in itself isn't so surprising, but the important thing is that complex structure is compatible with the Fubini-Studi metric. So it defines what I call a Fubini structure. And you can understand, this is such a simple example, you can understand what this complex structure is. It's just obtained by, at each point, by the fact that you fixed a point of CP2, which you're away from, namely Q. You've got another point. You want to know what is this Fubini, what is this new complex structure at this point? And the answer is you take the line joining P to Q, and that will split your tangent space at P into 2 one-dimensional subspace or complex one-dimensional subspaces, and you just reverse the sign of the standard complex structure on one of those. And the reason that's still integrable is related to the fact what we're really doing here is we're thinking about CP2 as just, if you remove a point, you can think of this as the total space of the line bundle, of the normal bundle over CP1. And so you have the standard complex structure, but you can reverse it on say, the fiber direction. And that will give you a non-Kähler complex structure. That's fairly straightforward, but then you can try and play the same game with other surfaces. And well, let's say, I know I'm running out of time. So I talked about these 1-1 surfaces. So in particular, I want to talk about these diagonal ones that corresponded to this diagonal matrix. If you do that, forget this for the moment. This is just a general chit chat about Del-Pezzo surfaces. And so if you take one of these diagonal surfaces just defined by this matrix 0, 1, lambda, then you can, that will define a 1-1 surface in the flag manifold. It will, because of because of the sort of homology, it will hit a generic twistor fiber in 2 points, but it may be that it contains some twistor fibers. Well, what happens? It doesn't actually in this case, but what I can say is the following. So this is quite a good. I'm glad I got to this point anyway. So for this particular type of 1-1 surface given by a diagonal matrix, remember, up to unitary equivalence, it turns out that we have this parameter lambda, which is like a cross ratio, remember. Lambda can't be 0, it can't be 1, because we want distinct eigenvalues to get the thing to be smooth. And if lambda is real, it turns out that there are infinitely many of these fibers, these twistor fibers of pi, which lie in our surface. And this infinite family of fibers, that just projects a circle inside CP2. If lambda is complex but not real, then it has no twistor fibers, but the 2 points could still come together. So instead of having 2 separate points, we could have the surface tangent to the twistor fiber, and the points in CP2 where it's tangent correspond to a smooth torus. But if you take the first case, it means that if I take CP2 and remove one of these circles, then I can find one of these 1-1 surfaces which maps by, well, it will then, it's of degree 2, but we can, once you remove a circle, you can split the surface S into 2 components. And if you just take one component, it would define a complex structure on the complement of a circle in CP2. And that's sort of interesting because a similar thing happens for S4. In fact, S4 minus the circle, which is like the quaternions minus a real line, has a very interesting, has a natural orthogonal complex structure that leads to the theory of quaternion slice functions. Slice regular functions. Okay, I'm gonna finish. So I just wanted to say that the case of these diagonal surfaces, there's also the Del-Pezzo surfaces. This is natural torus action. The maximal torus will act on these surfaces, preserving the surface, and so you can understand these circles in terms of the moment map to here I've got the moment map from CP2 to a triangle, and there are other problems also related to this real moment map and embedding the flag manifold into its real Lie algebra R8, and asking how many sets of equivariant points, mutually equidistant points we can find. Okay, that's it. I've run out of time. Let me just say what the game is. I won't show you any more than this. But the game in general is to take these surfaces and count, assuming that they're not real. So the example I gave when lambda was real, in which I had infinitely many twistor fibers, that can only happen if S is equal to JS. Remember, JS is anti-holomorphic involution. In general, you get bounds on these, the number of twistor fibers. And I'm not, the slides will only be available on my homepage. So if you're interested, you can look further. Let me just finish with one newer result that my co-authors found actually more recently. And that is this result here. I did a comparison with CP3, but that's work in progress. It's not, although these are birational CP3 and NF, it's not so clear how you can convert one theory to the other. But let me just leave you with this slide that shows sort of an upper bound on the number of twistor fibers in a smooth surface in the flag manifold of bi degree AB. And there's a lot more work to be done here, but it's an interesting game one can play to count these twistor fibers. Sorry, I must stop there. Thank you.
Thank you for a beautiful talk.